it will clash with them.
Sorry about that. Yeah, okay, now I'm, yeah. Okay, sorry about that. So this talk is about extending incorrectness logic with backwards reasoning. So let's say that you have a program that takes as input a list of elements, and it shuffles these elements into a new list. Let's then say that you want to prove, using a program logic, that indeed this program can produce at least all possible permutations of the input list. Or let's say that you have a program that computes a certain variable y with some convoluted expression or with some convoluted program, and you want to prove that at least the result y is 0 is possible. So this program may produce a lot of results, but at least you want to show that the value y is 0 can be reached after execution of this program. With standard Hoare logic, this is not possible, because Hoare logic expresses basically what can happen at most. If you have a triple P, C, Q, then Q states what can happen, gives an upper bound to the things that can happen from states that satisfy P. Instead, incorrectness logic reasons over what can happen at least. And you can see this from the definitions. So Hoare logic is defined as the post set of P is a subset of Q, meaning that if you start in states that satisfy P, you run your program, then you will always end up in a Q state. But incorrectness logic talks about what can at least happen, and it's formulated as Q being a subset of the post of P, meaning that for all the states in Q, you know that they are reachable by executing program C from a state that satisfies P. In other words, it shows a certain type of liveness, whereas Hoare logic shows a certain type of safety. And you can see this also from things like postcondition weakening versus postcondition strengthening. In Hoare logic, you can do postcondition weakening. You can weaken it all the way up to true. And that basically means then what you then say is, well, what can happen at most? Anything. And that becomes a trivially true statement. Whereas for incorrectness logic, you can do postcondition strengthening. And you can strengthen it all the way to false, basically saying that for 0 states, I prove that these are actually reachable. Now, with this question in mind of what can at least happen, how can we use this incorrectness logic? Well, the way that Peter O'Hearn uses it is that Q characterizes a bug, and we aim to prove existence of this bug. And that's why it's called incorrectness reasoning. So we want to prove that the program can at least exhibit the bug, and that means that we have no false positives. But in the reverse Hoare logic paper, it's also used as a correctness type of reasoning, where Q characterizes some form of specification, like with the shuffle function, and we aim to prove correctness with regards to that specification. And finally, we can also, the way we also want to use it is where we have some assertion in the program, and we just want to show, can we at least trigger this assertion? So with these use cases in mind, it makes sense to think of the following question. Can we now do backwards reasoning over incorrectness logic? In other words, if I give you a Q, this assertion or this specification or a characterization of a bug, and if I give you the program, of course, can we now define a function tau that takes these two as input and produces a precondition or presumption, such that an incorrectness triple holds? In other words, can we go from an assertion back to the entry point of a function or of a program? And the answer basically is, well, no. And to see why, let me use an example. So here we have a very simple program. Y gets assigned x plus 1. And we want to see whether states where y is equal to 10 are reachable after execution of this program. And I think everybody here would say, well, sure, this is reachable. Just start from a state where x is equal to 9. But that is not a valid incorrectness triple. As a matter of fact, for this result, there is no correct incorrectness triple. And the reason is that incorrectness reasoning treats the result as by saying that all result states should be reachable. And y is 10 formulates a large set of states, because it also formulates states where y is equal to 10, and for example, x is equal to 0. And that state is not reachable. If I would want to prove that states where y is 10 are reachable using incorrectness logic, then I would have to have started with a result y is 10 and x is equal to 9, and then I could show that these are reachable from a state where x is equal to 9. But this is, of course, very unsatisfactory, because if I want to characterize some bug, what this basically means that I would have to start from a result or a postcondition that precisely defines constraints over all variables in the state. And that's just infeasible and impractical. So I don't want to need to define anything over x if I just want to know whether states where y is 10 are reachable. So what we added to incorrectness logic is a notion of underspecification. And it allows you to say, I want to look at states where y is 10, and I want to see if those states are reachable. And I treat x, I underspecify variable x, meaning that x is irrelevant. So this triple holds. States where y is 10, where I don't care about x, are reachable from some state where x is equal to 9. As a matter of fact, I can make it stronger and say states where y is 10, where I don't care about x, are reachable from some state where x is equal to 9, where I don't care about y. The value of y is irrelevant because no matter what value it has, the result will be reached, since y is going to be overwritten anyway. So this enables backwards reasoning. So what we have actually contributed is that we have extended incorrectness logic with this notion of underspecification. We have then built this proof system that you see here on the right-hand side of the slide. And this proof system is constructed in such a way that in the conclusions of all these rules, the result or the postcondition is just some q. And it shows how you can go from this q to a presumption or precondition. In other words, it can be used to do backwards transformation. Of course, we have proven soundness of this proof system, which in this context means that triples hold, or in other words, that there are no false positives. We have also proven completeness for a subset of programs and predicates. And the exact definition of that is, of course, in the paper. Finally, in order to put this in practice, we have defined some proof tactics. One of them has to do with finding the right values to instantiate these rules. And we show how SMT solvers can be used for that. And the other one is how to treat with loops. And I'll talk about that a bit more. Finally, we have an implementation of a prototype and applied it to get some experimental results. So let's take a look at one of these rules. I think actually for this proof system, the assign rule is the most interesting one. So here you see it on the top of the slide. And the first thing that you see is that there is a bit of, let's say, management of which variables are relevant and irrelevant. So let's say that I have a variable x that is considered to be irrelevant. And it's used as an input for computing a value for y. So the y is going to be assigned f of x. If the value of x is irrelevant in the conclusion, then it's going to be relevant in the presumption, because its value is I need to define constraints over this variable in order to make the result reachable. But y itself is, so x is removed from the set of irrelevant variables, which happens here. But y is added to the set of irrelevant variables, since it's going to be overwritten anyway. Then, how to now actually compute a presumption from a result? Well, at the heart, it's just standard substitution, as the way it is with standard Hoare logic. So in Q, you do substitution, where you replace occurrences of y with what it gets assigned to. But there's more to it. First of all, there is a side condition. So the side condition states that the result Q should be sufficiently strong to prove that Y is in the image of F. So why is this? Well, if this is not the case, that means that Q models some state where Y is not in the image of F. In other words, Y cannot be computed using this function F. It cannot possibly be an output of function F. And that would mean that Q models at least one state which is unreachable. And since incorrectness logic reasons over triples where all result states must be reachable, this side condition is necessary. Now you can see that there's still more to this one rule. And to explain the rest of this rule, I need another example. So here we have an example where Y gets assigned to x plus 4 modulo 7. And now I want to see whether states where Y is equal to 4, whether those are actually reachable. So they are reachable. So for example, from a state where x is 0, if I then do x plus 4 modulo 7, I get into a state where Y is equal to 4. Now if I would do standard substitution, then what I would get as a presumption is the set of states where x is either 0 or 7 or 14, etc. X is 0 modulo 7. That's what I would get if I would just do standard substitution. But that is a large set of states. X can be either 0, 7, and so on. And since we are talking about reachability, it suffices to find only a subset of that states, because I only need to find basically one path that that triggers the result. So here I want, instead of formulating that x is 0, 7, 14, etc., I want to be able to prove that just the state x is 0 can trigger this result. So that's called zooming in on a specific value. And this is more than just for sake of, let's say, completeness of the logic. It's even more than for sake of precision. It's actually crucial that we can do this for the sake of composition. Because if you want to use this established triple compositionally, then it may be hard or impossible to show that states where x is 0, 7, where all those states are reachable. It may be the case that they are not all reachable, whereas if I zoom in on this specific state, that state may be reachable. So the rule supplies you can instantiate this rule in such a way that it allows you to zoom in on specific values of variables. So then the while rule. Now I won't explain it in all detail, but what's most important here is that similar to the zooming in that I just explained, since we are talking about reachability, we don't necessarily have to have loop invariance. If the result is reachable after 0 executions of the loop, then you can just treat the loop as a no-op and just see if, well, then prove reachability in that way. In other words, the while rule requires you to find an iteration count of how many iterations the loop body is being executed. And in order to find these iteration counts, we found that the concept of loop summaries is very useful. So these loop summaries, they basically summarize the values of certain variables in the nth iteration with a closed form expression. Now we have done an evaluation. We have used the svcomp benchmark suite. And this was very useful for us because this actually comes with a ground truth. So it contains a lot of programs. These are categories of programs. And for all these programs, they contain assertions with annotations whether these assertions are reachable or not. And in that way, we could first evaluate soundness. So if the assertion is known to be unreachable, do we actually generate an unsatisfiable set of side conditions and a presumption? Now, of course, since we have proven soundness in the Isabelle theorem prover, the percentage of functions for which this holds should just be 100%. We are sound, so it should simply be 100%. But you can see in the highlighted column that this is not the case. Actually, it's very often below 100%. And the reason is that these programs contain certain constructs that we do not support yet, such as floating point computations or variables in loops that we could not summarize. And what we have done is that we have treated those constructs over-approximatively, saying that basically those variables, anything can happen to them. And that causes, then we proceeded with the presumption generation over the parts of the state that we could deal with. Then what we also want to evaluate is a certain type of preciseness. So if you think about it, we are trying to do reachability, and we could have just done sort of fuzzing, right? Where you start basically from any state, take true as a presumption, and compute the post set from there. Instead, we do this backwards reasoning that gives us a presumption, and we want to show that this presumption is actually significantly smaller than just the entire set of states, the entire set of initial states. And this, so we have measured this reduction factor and found that this actually, that the generated presumption very often is significantly smaller than just doing fuzzing. Now, as next steps, one of the things that the table that I've just showed shows is that we need better loop summarizations. So we have implemented sort of a naive technique that only deals with linear variables, and with stronger loop summaries, we would be able to capture more variables, and that would lead to better results. I want to be able to apply this kind of reasoning actually to more lower level code, for example, LLVM, and then we get into challenges that in lower level code, point arithmetic often becomes very complicated, and that there's just an absence of actual syntactic control flow structures. Instead of while loops and if statements, you have a control flow graph, and it's not always possible to just transform a control flow graph back into syntactic control flow structures. And the final thing is that in order to make this scale, I want to have a compositional approach with respect to function calls. And of course, this sort of shouts that we should do separation logic. And I'm really interested in seeing how the notion of underspecification of variables combines with separation logic and incorrectness reasoning. So with that, I conclude and want to thank you for listening.
All right, we have time for one or two quick questions. What?
Correct me if I'm wrong. Is it fundamentally boiled down to the invertibility of the functions? So if you have in your example, you have function f, if it's non-invertible, how does it work?
So let me show the rule here. So if I heard you correctly, the question is like, well, if f is not invertible, how does it work, right? So indeed, the rule requires you to find an inversion of f. Exactly. If you cannot invert f, then you cannot apply this particular rule. So then it would not work. Yeah.
So your theory is sound on the assumption that the function is only invertible.
Yeah, exactly. Yeah.
Last, yeah, question back there. Quick one.
Thanks for the talk. So when you had the example, the motivating example as the start, I just thought you could use Lisbon logic, or also called sufficient incorrectness logic. So what would you say are the advantages of your approach?
Yeah, so Lisbon logic formulates another type of sort of reachability, right? Where you say that all states that satisfy the precondition will lead to the postcondition, whereas incorrectness logic says that all states that are modeled by the postcondition are actually reachable. I'm not here to argue which one is better, or, I both have their use cases, obviously. I actually think that this is a particular example which actually highlights specifically incorrectness logic, where you would want to say, well, I want to prove that all possible permutations are really reachable. And I think this is something, if I'm correct, that you cannot do with Lisbon logic.
All right. Let's thank Freek again.